Good day. Today, we want to talk about a fundamental the theory in calculus, which is known as derivative of function. So, derivative of function occur when we have a curve on the xy plane, a curve f of x on the xy plane. If you are to find the slope of this function at a point A on the horizontal axis, okay, so if you measure the point here, so the corresponding f of A is there. So if I will find the slope at any point of x, let's say we have a point of x here. Of course, definitely the point is measured as f of x here. So if you have to find the slope from this point to this point, okay, so we are going to have what we refer to as a change in x here, and we also have a corresponding change on the vertical axis. So literally, when we say the slope of this function, the slope x of this function is given as the change on the vertical axis minus the change all over the change on the horizontal axis. Okay, so this is known as the change in the vertical and the change in the horizontal. So, however, if you are looking for a total change here, okay, so as this x tends to a, okay, so what we get is a total change, okay. We denote this by dy dx, okay, that is total change in y all over the total change in x. So this will be equal to the limit as this xa tends to a f of x minus f of a all over x minus a. So this formula is what we refer to as derivative of a function, otherwise known as the slope of a function. Okay, so because this notion or slope occur in many fields of science and engineering, we give it a general, there's a general look we give to this definition. That is, if we let the change in x here to be a letter h, that is, if we let h to be equal to x minus a, okay, yeah, because x is tending to a, then what you have is h tends to 0, because when a comes to this place, okay, it becomes x minus a, and we are letting that to be h. So as h tends to 0, okay, of course here also we can make x a formula. We can make x a formula. So here also x becomes a plus h. So we can now redefine this definition as the following formula. So we now have the total change in x, which is also referred to as f prime of a. This time we call it f of f prime of a, and this will be the limit as h tends to 0, f of, don't forget we are replacing x now with a plus h. So this will be a plus h, f of a remains all over h. Recall that here we initially have x minus a here. So the formula of find derivative of a function can also be given as this, where this formula is referred to as the derivative of a function at a particular point x equal a. Okay, so if this limit exists, so we say the derivative of a function f prime of a, or the slope of a function at the point a exists. Okay, so let's give an example of this. Later we'll now give a general notion of this equation. So for example, we want to find the derivative of a function at a particular point. Okay, or generally, let's say at x equal to a. Find the derivative of f of x equal to x squared minus 8x plus 1. Okay, at the point let's say 1, x equal to a, 2, x equal to let's say x equal to 1. Okay, so we want to find the derivative of a function when x is equal to a, and then secondly when x equal to 1. So solution. So recall in the formula that we have what we call f of a, and we have f of a plus h. So we can get those two terms from here. So firstly, if you say f of a means that whenever we see x, we should plug a. So this will be a squared minus 8a plus 1. Okay, also we also have the term f of a plus h. Okay, this also means whenever we see x, we replace it with a plus h. So this becomes, here we have x squared, so we are replacing it with a plus h. So this will be a plus h squared minus also another x here, a plus h, then this is a constant, so plus 1. So therefore, the derivative of a function for 1 now, when x equal to a, will be given by f prime of a. This is also known as dy dx. Don't forget. So we can call it f prime of a because we want to evaluate at the point x equal to a. So in the formula, we have the limit as h tends to 0. Then we have this term f of a plus h, okay, minus f of a. So if you substitute these two terms, so we have a plus h squared minus 8 into a plus h plus 1 minus f of a, which is given as this. So everything over h. So next is to simplify this term, okay, after which we will apply this limit on the simplification format. So we are taking this up. We are taking the simplification up. So this will be equal to, of course, we have f prime of a will be equal to the limit as h tends to 0. So if you open the bracket, this is a squared plus 2ah plus h squared Then let's open a bracket here. This will be minus 8a minus 8h plus 1, then minus a square plus 8a minus 1. Everything over h. Okay? So here, we see that sometimes are alike. For example, we have a square here, positive a square, negative a square. These two terms will take care of one another. Okay, we also have negative 1 and positive 1 here. This will also take care of themselves. Again, we have negative 8 plus positive 8. This will also take care of themselves. So the remaining terms will be the limit as h goes to 0, 2ah plus h squared minus 8h, everything over h. Okay, so a also, we'll see that there exists at least one term of h in the numerator. Okay, so we can factor one of the term out, which will eventually cancel this. So this will be equal to, let's remove h out, then one of it will, the one h that is out will cancel this. So, okay, let's do this. Let's do this here. So this will be equal to the limit as h tends to 0. So we are factorizing h out. This will be 2a plus h minus 8 all over h. So this h takes care of this. So the remaining term here will be, so we can now apply this limit on this term, on each of these terms. So recall that this is 2a. This 2a is independent of h. So this limit will not affect this because this is a parametric constant. Okay, this is h, of which this will affect this, and this is 8, which is also a constant. Okay, we have earlier said in our previous video that the limit of a constant is a constant, just like this. So here we have 2a, this will be 0, okay, minus 8. So this is equal to 2a minus 8. Okay, so this is a derivative of a function x squared minus 8x plus 1 at x equal to a. Of course, if a is finite, we'll see that the limit, this limit that we have done exists. Okay, so for the second one, is the same process. Okay, so we can use this, we can use exactly this formula for it. That is, what the second example is saying is that if we replace a with 1, okay, if you replace a with 1, what will be the value of the derivative? Okay, will the derivative exist? So let's see that quickly. So for the same example, so but this time we are evaluating at when x equal to 1. Okay, so that's example 2. Okay, of course, since f of a is given, since f of a is given as, since f prime of a is given as 2a minus 8, so then f prime of 1 will be equal to 2 into 1 minus 8, and this will be 2 minus 8, and this is minus 6. So the derivative of a function x squared minus 8x plus 1 at the point x equal to 1 is given as negative 6. Of course, negative 6 is finite, and the derivative of that function exists at x equal to 1. So this is how we use derivative of a function, at a particular point x equal to a. Now let us now give a general notion of what a derivative is. Okay, so if you are to find the derivative of a function at any particular point, okay, so this is how we define this. So definition, we say a function f of x is said to have a derivative for all x in the domain of R if, that's this time we call this f prime of x. Since we are evaluating this for let's call it any, for any value, for any x in R. Okay, so here this will be, instead of x, instead of a here that we have in the earlier formula, okay, it will be x, because a connotes a particular point, while this x connotes any point. So x is a variable in this case. So this will be the limit as h tends to 0, f of x plus h minus f of x all over h. Okay, so this is what referred to as the derivative of a function at any point. So if the limit exists, we say the derivative of this function exists. Okay, so example that these are numerous is similar to the first example we consider, just that this x connotes any variable x. So let's give an example under this. Okay, the first example we want to consider that this is a polynomial, a general form of a polynomial function. So the derivative of it. Okay, so example, find the derivative of the following functions. So one, when we have f of x equal to xn, and two, okay, let's consider a logarithm function in x. Okay, this is a general form of a polynomial where n is a positive integer. Okay, for this example, n is a positive integer. Okay, I want to find the derivative of this function. Of course, the derivative of the function exists at the point x greater than 0. Okay, so the condition we must impose on this is that x is positive before we can find a derivative for this. Okay, so let's take this one after the other. So for the first example, we are given f of x equal to xn. Here the corresponding f of x plus h will be, at least whenever we see x, we put x plus h. Okay, so this is f of x plus h will be this. So therefore, f prime of x will be equal to the limit at h tends to 0 Okay, from the formula we have that this, which is x plus h raised to the power of n minus xn, everything over h. Okay, so we'll see that this term is a binomial term. Okay, so and of course we can use the formula of the binomial term, which says if you have two binomial terms with the power n, we can rewrite this using binomial expansion. Okay, the binomial expansion is given as solution which has this way to n combination r x raised to the power of n minus r b raised to the power of r. Okay, okay, so this term alone, okay, means this term. Okay, and this is minus xn, everything over h. Okay, so this is equal to the limit as h tends to 0. Sorry, this is h, not this is h according to this. Okay, so if we express the first term of this function, the first term of this is that is when r is 0. We have n combination 0, that is 1. When we put 0 here, that will be x raised to the power of n. Okay, it will be, sorry, that will be x to the power of n, that's n minus 0, then h to the power of 0. So this is 1, this is 1 for the first term. So here we have this. Okay, let's express the first two terms of this. Again, when r is 1, okay, we have n combination 1. A number combination 1 is the number, so that is n. Okay, so here we have x raised to the power of n minus 1. Okay, then h raised to the power of 1, that is h. Okay, so the remaining term will be solution r equal to 2 to n combination r x to the power of n minus r h raised to the power of r minus xn. So everything here over h. Okay, so what we have done here is to express the first two terms of this series, which is s raised to the power of n plus n multiplied by x raised to the power of n minus 1 h. Okay, so here we see that some of the term of h, the power of h is increasing because when r is 2, we have h squared here. When r is 3, we have h cubed. When r is 4, we have h raised to the power of 4 up to the degree n. Okay, so here you will see that the first term here is the same term as this. This has a positive and this has a negative. So these two terms takes care of one another. Okay, and we are left with we are now left with the limit as h tends to 0. Okay, so we are left with this plus, okay, this term has gone, so we have this plus this term. Okay, this term is r equal to 2 to n combination r x to the power of n minus r h to the power of r. Of course, I'll start from 2. Okay, the power of this is increasing, not that. Okay, this means h appear at least, okay, twice, okay, off. Okay, so this has gone, so we are now left with h. Okay, so in all of this, so we see that h appears throughout, okay, from even from the series. Okay, so it means we can factor one h out, which will cancel this. Okay, and this will be equal to the limit as h tends to 0 x to the So we are factorizing h out. This will be n x n minus 1. So this h is out. We are factoring one h out from here. Okay, and because of that, this will be r equal to 2 to n combination r, x to the power of n minus r. Since we are taking one term of h out, this h will be raised to the power of r minus 1. Okay, and of course, everything over h. Okay, so here again, this h will cancel this h, and this will be equal to the limit as h tends to 0. H cancel h, meaning we have nx raised to the power of nx raised to the power of n minus 1 plus summation r equal to 2 to n. So n combination r, s raised to the power of n minus r, h raised to the power of r minus 1. Okay, so this limit affects all what is there. Okay, so now this term is independent of h, and of course this looks like a parametric constant. So this limit will not affect this, but this limit will affect all this because there exists at least 1 h here. When we substitute r to 2, we are particular about this h because the limit here says h tends to 0. Okay, it means if you substitute 2 here, at least we have 1 h in the series that this limit will affect. Okay, so and because of this singular thing, this will make the entire list 0 because in each term of the series we have the letter h. So this is nx. So this limit will not affect this, but this limit will affect this. Okay, so if you substitute 0 here, this will make the entire series here 0. Okay, because of this h. Okay, and eventually this will be nx n minus 1. Okay, so therefore the slope of the polynomial xn, okay, the slope of this is nothing but n x raised to the power of n minus 1.